Greetings everyone, thanks for coming. Today I'm going to share our recent work on understanding and enhancing slow fault tolerance in modern distributed systems. So distributed systems actually lie at the heart of today's digital infrastructure. However, failures can and do occur in various forms such as fail slow and fail stop. So in this talk, we're going to be focusing on one type of novel and understudied failure model called fail slow failure. A fail slow component is one that is still functioning but with lower than expected performance. In practice, fail slow failure is actually a severe problem where it can cascade from a single device level failure to node level or even cluster level shutdown. And also fail slow failure is not uncommon. According to a recent study from production, annual fail slow failure rate is as frequent as fail stop incidents. And more importantly, traditionally, when we are designing a certain system or some monitoring stacks, we commonly assume that the system components should follow a binary fault model where these components should be either correct or stopped. However, fail slow failures often manifest as kind of a performance issues which fall right between them. So in this case, studying the slow fault tolerance of modern distributed system is vital. However, the most recent study is from like almost a decade ago, and it's focusing precisely on fail slow hardware. And in that study, we're actually performing a fault injection study which assumes a worst case scenario where the slow faults they injected are up to, like, for example, 1,000 times slowed down, and they assume that the slow faults will persist throughout each injection test. However, through like almost a decade study, we understand and characterize slow faults as a way more complicated fault model. And more importantly, through a decade's advancement and development, both the landscape of hardware and software have been changing to blazingly fast. In that case, we're interested in what is the slow fault tolerance, how to characterize it in today's modern distributed systems. So in our work, we study 6 widely used distributed systems, and we use their latest stable version to incorporate the latest code fixes. And these systems cover diverse services, and we use cloud benchmarks to test them with distinct workload patterns. And before we dive deep into our first study part, there's a big question, is that actually evaluating the slow fault tolerance or like evaluating how slow faults impact a certain system or how a system reacts to slow faults is hard. Like on one hand, slow faults are multifaceted. Like slow faults have a lot of attributes. It can have different severity types, location. Here, location means it could be injected to or affect a follower node or leader node in a quorum-based system. And also we have other attributes like start time and duration. And added them up together, we may end up with like kind of hundreds of thousands of combinations to test. And on the other hand, it is hard to quantify the impact of slow faults. For example, to what extent does a 1 second network delay incur to a system compared to like a 10 millisecond one or a 100 microsecond one? So in this case, our first contribution lies here. So we propose a slow fault injection testing pipeline, and this pipeline enables us, first of all, to do some automated testing that ease the testing of hundreds of thousands of combinations of slow faults. And secondly, we can ensure a high coverage of slow faults in the real world. We can actually consider the multifaceted nature of slow faults. And lastly, through this standard, like kind of a standard structure, standard pipeline, we can easily calculate the percentage of performance degradation before and after slow fault injection and use it as a primary metric to measure slow fault tolerance. And in that case, we can enable a fair comparison across different combinations of slow faults or across different systems. Now, with this automated testing pipeline at hand, we're able to do a lot of interesting stuff. And in summary, we have conducted a comprehensive study and come up with around 9 primary findings. And we actually find that slow fault tolerance of distributed system is a highly nuanced thing. It is highly sensitive to the deploy environments and the slow faults themselves. So I'm going to start with the deploy environment. So let's start with let's get back to the game. So when developers, first of all, they develop a certain distributed system, and their system will be used in the future, deployed, managed by operators or end users. However, at the time of deployment, it is hard for a developer to anticipate things. For example, it is hard for a developer to anticipate how their system will be deployed, for example, under what hardware environments, resources, under what software configurations. And also, it is hard for them to anticipate what workloads are running with distinct I/O patterns by the end users, by the operators. So in that case, at the time of development, when we are developing the fault-tolerant countermeasures, it is hard for them to anticipate things. So from this starting point, we want to evaluate is slow fault tolerance sensitive or related to the different given hardware resources, different software configurations, or the unforeseen real-world workloads. So in this talk, due to time constraints, I'm going to cover the most interesting one that I think is about the configurations part. And you're also welcome to look for the paper for more detail. So our first question is, does tuning software configurations help to improve a system's tolerance to slow faults? So in our study, we take HBase as an example, using a keyword-based search for all possible slow-related configurations. These configurations are directly related to, for example, the detection, the threshold of a certain slow request, slow operation, and so on. And since slow fault tolerance can be later studied, they're kind of they can also be affected by different slow fault workload and resources. So these are also the factors that contribute into a sensitive slow fault tolerance. So in that case, we want to control them in a static setup, and then to systematically study the impact of tuning software configurations. So in total, based on these static setup, we have come up to around 8,000 combinations of different configurations, and we are interested in whether, for example, some configuration can help to improve a system's slow fault tolerance. Actually, it helped. So under a fixed setup, without tuning the configuration, if you are using just the default values for each configuration, HBase will suffer from a 98% degradation under some static setup. However, we're actually seeing some configuration that after fine-tuning them, they can actually help the system to reduce the degradation to around 20%. So, however, so in that case, we want to pick the optimal configuration in the last step under the static setup, and then we try to and test it under a more dynamic way under different workloads. So previously, we're actually fine-tuning our configurations based on one workload setting, which is the one that with the 8 client threads. And however, when we increase the client threads to 32 threads, for example, it is not always optimal. Previously, suboptimal one actually yields the lowest degradation when we are changing the workload to a heavier one. And more importantly, when we're conducting experiments, you can see the error bars here. That means that we are repeating each set of experiment for 50 times to ensure generalizability. And when commiserating experiment data, we observe that some of the runs are actually the cluster or the node is failing. Which means that if we fine-tune a configuration based on a static timeout, these configurations actually overfit with a specific static setting. And once we change the workload to a more, for example, more heavier one, the previously optimal setup overfit, and then kind of oversensitive to the workload changes, and then it kind of harms the availability. So in conclusion, we find that if we want to by tuning configurations to improve slow fault tolerance, we can only do it to benefit under a static and controlled setup. And in reverse, if we just rely solely on fine-tuning the configuration, will kind of make the system's slow fault tolerance fragile. We also, together, we remember that we mentioned about the different deploy environments. So we also have the resources, which means, for example, different CPU cores and memory sizes assigned to each distributed instance. So we find that scaling up resource improves performance, but adversely expands the impact of slow faults by up to 10 times. And for workloads, we identify common danger zone which exists commonly in distributed system where just a slightly heavier slowness injected would incur a significantly higher degradation. And this standard zone can be potentially leveraged to early detection and early alerting of these performance issues. So if you are interested in this, please refer to the detail in the paper. And the second half of the study that we perform is that we want to investigate whether slow fault tolerance is sensitive to slow faults themselves. And that is done by using our testing pipeline. We use some injection tests and generate real-world slow faults with different attributes. And I'm not going to cover all of them. And one of the findings here is that, so we're using the testing pipeline to inject slow faults with different severity and different locations. So here, location means that we actually inject the slow faults to the follower node or the leader node. And as we can see here, it is kind of counterintuitive, as a slow follower is actually more harmful than a slow leader. So this is counterintuitive, as in a quorum-based system, slow follower should not incur such more damage. And due to the time constraint, I'm not going to cover the whole investigation process, but in the end, we find that this is due to the bad detection of heartbeats or keep alive ping, which is basically essentially static timeouts. And these static timeouts cannot accommodate to the dynamic and continuous nature of fail slow or slow faults. And so next step, we try to identify, in the code level in practice, how do developers detect slowness for slow operation, slow request in the code level. So let's start with an example from HBase. So in HBase, the developers, so here the system variable is called sync time. And it will first check whether the sync time is slow by using a warning threshold, using an if condition. And if the sync time exceeds a certain threshold, it will trigger some warning action, which is just some logging. And it will also maintain a counter to count the number of triggering. And if the sync time is even worse, it's more slower than a fatal threshold, or the warning count exceed the warning count, it will trigger a fatal action. So this is actually commonly adopted in today's distributed system fault detection or alerting. We find that these static thresholds are set over conservatively from 100 milliseconds to 2 minutes. However, in our early exploration, we find that even the 100 millisecond network delay would cause the system to incur more than 50% degradation. So in this case, these over-conservative thresholds are actually too late. We also find that the state-of-the-art slowdown tolerant protocol, which is published in OSDI 20, it also suffers from static timeout. So we're using Copilot to compare with two of its baseline called multi-pixels and 8 pixels. And we find that it's only optimal under a 10 millisecond network delay. And the reason is because it sets a fast takeover timeout, which is equals to 10 milliseconds, which means that when the network delay injected is lower than 10 milliseconds, Copilot just waits and endures the slowness. And when the injected delay is above 100 milliseconds, it is controlled by the heartbeats set by Copilot, and the Copilot just simply waits between 100 milliseconds and 1 second. That means Copilot still suffers from the static timeout. So in conclusion, static thresholds and slow faults have a lot of conflicts here. And traditionally, when we use static thresholds to detect failure, it works for fail stop, because fail stop failure is it has a clear boundary to distinguish, and those over the conservative static thresholds will do. But for fail slow is a non-binary and a dynamic fault model. In that case, these hard thresholds won't work well, and we need to make the failure detection logic adaptive. So in the later part of the work, we proposed ADR, adaptive detection and runtime, which, so due to time constraint, I'm going to cover this part quick. So developers already have implemented a lot of detection logic, for example, using some if condition. And in that case, since the static threshold is kind of over-conservative, how can we make this threshold adaptive? So our solution is very straightforward. We can just maintain the sliding window of the historical value of the certain variable, and we can use some simple statistics. For example, here, 99 percentile as adaptive threshold, because it fits with the data. And in this case, we have two problems. First of all, P99 means that we always have 1% false positive, which could be potentially noises. And Secondly, how can we distinguish from real slow faults from messing up with some normal workload variations? So we observed that the workload variations can be actually well described by another attribute of the variable called update frequency. Due to time constraint, I'm going to cover this fast. So for example, under heavier workloads, frequency will increase, which indicates we assume a workload increase and just a normal variation, and so there's a lighter workload. And in the end, only when the frequency decreases and the value oscillates can we assume this is slow fault. So this is kind of a deficit detection. We also, and ADR can also be used as a plugin by using some simple APIs. And in the end, during evaluation, we find that with ADR, it can actually help to reduce degradation by up to 90%, and we can achieve a timely detection in seconds, and also a minimum 2.8 average overhead. So, so in conclusion, we find that first of all, slow fault tolerance is a highly nuanced and sensitive thing, and detecting slowness with static threshold is insufficient. So, and in our work, we propose a testing pipeline and ADR to help address it. Thanks. I'm more than happy to take any questions.